All right, we are now going to use this new tool that we've just learned for limits to help us compute integrals where we're asking a question about infinite behavior. In particular, we're interested in looking at integrals where one of the bounds is infinite, or maybe even both bounds are infinite. Or maybe it's not that the bounds are infinite, but the function itself has some kind of infinite behavior inside the interval where we're integrating. So for example, this one, as x approaches 0, 1 over root x goes to infinity. So as we approach this, we're going to have an infinite bound that we have to deal with. Or maybe it's not at the boundary points of the interval, but it's in the middle. Because when x gets close to 0, 1 over x squared blows up, but 0 is trapped in the middle of this integral to find the area. And so it's going to mess up what the actual area under the curve is, because we have this point of discontinuity inside our integration. So for all of these, we have to use limits to deal with what is unpleasant. In general, if one of your bounds is infinite, the first step is just going to be to replace that infinite bound with a limit statement. So instead of worrying about what 1 over x does from 1 to infinity, we're just going to integrate from 1 to, say, a, and then we'll let the limit happen when a itself approaches infinity. And we're still doing the integral of 1 over x dx. So infinity up here gets replaced by an actual number. And then after we do that integral, we ask, does this limit converge? And if it goes to a number, we're going to say that the improper integral converges. And if it diverges, we'll just say that the infinite integral diverges. Let's just do this one. We're integrating 1 over x. Great, we know how to do this. So this will be the limit. A approaches infinity. Antiderivative of 1 over x is the natural log of x, and we're going to go from 1 to a. So proper integrals, we plug in 1, then we plug in a, and then when we subtract, we plug in 1. So this will be the limit as a goes to infinity of the natural log of a minus the natural log of 1. The natural log of 1 is 0, so we're looking at the limit as a goes to infinity of the natural log of a, which of course is infinite. So because this limit is infinite, we will say that this improper integral diverges. This diverges to infinity. OK, so that makes sense. We would expect that an infinite area that looks like this would actually be huge, and it keeps going, so it goes to infinity. Great. Let's take a look at the second one. Right? Integral from 1 to infinity of 1 over x squared dx. We didn't change much. We just changed 1 over x to become 1 over x squared. So we're going to set it up the same way. We're going to take the limit. A goes to infinity of the integral from 1 to a of 1 over x squared dx. This will be the limit as a goes to infinity. Antiderivative of 1 over x squared is negative 1 over x. And we're going to evaluate this from 1 to a. Have to think for a second. So we add 1 to negative 2 becomes negative 1. And then we divide by that negative 1, which is where this negative comes from. So now that we have our antiderivative, we're going to plug in a. And then we subtract when we plug in 1. So this will become the limit as a goes to infinity of negative 1 over a minus negative 1 over 1. Now as a goes to infinity, 1 over a goes to 0. So this actually becomes 0. And minus negative 1 becomes positive 1. So strangely enough, both of these curves look similar, but this one goes to 0 much faster than this one. In fact, it goes to 0 so fast that the whole area from 1 to infinity is exactly 1. So this gives you the area is finite, even though the picture looks like you have this thing that never ends. It never actually touches the x-axis. So more strangeness can occur, and we're going to keep going. Let's look at the third one. The third graph also looks something like this. So let's see what this does when we do the same process. All right, let's look at the limit. Let's look at the integral from 1 to infinity of the natural log of x over x squared dx. First step is to write this as a limit. Limit as a goes to infinity of the integral from 1 to a of the natural log of x over x squared dx. So we'll take the limit as a goes to infinity. Now, how do we find the antiderivative of this thing? Oh, this is a little bit tricky. It looks like we're going to have to use integration by parts. We're going to have, let's see, looks like u is going to be the natural log of x. Oh, that's actually going to be dv, because no, that'll be u. Because the derivative will be 1 over x, which means dv is going to be 1 over x squared. So du is going to be 1 over x, and v will be negative 1 over x. Right? Antiderivative of 1 over x squared is negative 1 over x. So this doesn't look half bad. We have bounds, but we'll just leave them. So our integration by parts becomes u times v. So we're going to get the natural log of x times v, and negative 1 over x that we're going to evaluate from 1 to a, minus the integral from 1 to a of v du. V du, we're just going to be multiplying these two. We're going to have negative 1 over x squared dx between the two. So integration by parts gives us this really weird-looking result. I'm going to erase my u dv v du so that I can keep going down, because this is actually kind of interesting. So let's plug in our values. Let's evaluate at a and b, and then take the antiderivative here as well. So we're going to get the limit as a approaches infinity. When I plug in a, I get negative natural log of a over a. And then when I plug in 1, natural log of 1 is 0. So I'm going to get 0 times negative 1, which is 0. So I subtract 0. Plus, minus minus becomes a plus. The integral from 1 to a of 1 over x squared is negative 1 over x. And this is going to be evaluated from 1 to a. So this piece is not looking too bad. When I plug in a here, I'm going to get the following. The limit as a goes to infinity, negative natural log of a over a, the 0 goes away, minus 1 over a, minus negative 1 over 1. OK? And now we have to do the limit. Limit as a goes to infinity, this is going to go to 0. This here is going to be 1, and we just have to deal with this. This is the form infinity over infinity. So we can use L'Hopital's rule. This becomes the limit as a goes to infinity. By L'Hopital's rule, the derivative of natural log of x is 1 over x, so I get 1 over a. The derivative of a is 1, and I still have my negative. Minus 0 plus 1. And as a goes to infinity, 1 over a goes to 0. So this collapses to nothing, and I get 1. So this whole integral from 1 to infinity of natural log of x over x squared also converges to 1. So this is 1, and this was infinity. And as you can see, L'Hopital's rule shows up sometimes when you're actually evaluating the limit piece of the antiderivative. So this one was really fun because it uses multiple rules, multiple different things that we saw in order to find an actual area. Let's take a look at the last two because they're a little bit different. Integral from 0 to 1 of 1 over root x dx. At 0, we can't plug in, so we have to write a limit. This is going to be the limit as we'll go with b goes to 0 from the right, because the interval goes from 0 to 1, so we'll approach 0 from the right-hand side, and we'll do the integral from b to 1 of 1 over root x dx. So now b is never 1. It's never 0. It approaches it, but it never is. So we can actually do the antiderivative here. So this will be the limit as b approaches 0 from the right. Antiderivative of 1 over root x is going to be negative root x. And we're going to evaluate from b to 1. I'll need this piece. And so now we plug in. So we're going to have the limit as b goes to 0 from the right. Negative 1 minus negative b. Why do I have a negative? I shouldn't have a negative here. The derivative of root x is 1 over root x. This is a 1. This is a 2. Not a 1. Sorry. The antiderivative of 1 over root x is 2 root x, because the derivative, this is x to the 1/2, becomes 1/2 x to the negative 1/2. The 1/2 of the 2 cancel, and we get this. Sorry about that. So I could tell it was going wrong because I was getting a negative area. So I have a 2 root x. So we have 2 times root 1, so that gives me 2. And here I have limit as b goes to 0 plus, and we have negative b. As b gets to 0, here we don't have an issue. We can plug in 0. And so we get a total area of 2. So the integral from 0 to 1 of 1 over root x is just a full area of 2. If you look at the graph, 1 over root x just looks like this. So it's saying that this area here is going to be exactly 2. For the last piece here, I'm going to make a separate video about it because it actually is interesting. There's something non-trivial happening here. So I will see you in the last video where we integrate from -1 to 1, 1 over x squared dx. See you there.